Hello, everyone. Welcome to my YouTube channel, A Tech Hub, where we simplify technology, education, and smart learning for everyone. We have a fantastic topic for our deep dive today, one that really gets to the core of what makes modern web apps feel so incredibly fast.
That's right. And our mission today is very specific. We're going deep into the mechanisms that make frameworks like React so performant. We're talking about the virtual DOM, reconciliation, and the real game changer, the fiber architecture. These are the algorithms running everything behind the scenes.
Exactly. So if you've ever wondered how these huge, complex apps can change state without a single page refresh or, that annoying stutter, this is where you'll find the answer. We're basically decoding the engine. And if you find this video helpful, don't forget to like, subscribe, and share it with your friends. Your support really does motivate me to bring more useful content for you. Now, before we get to that shiny new engine, we should probably talk about what it was built to replace.
We have to. We need to start with the original problem, which is the document object model, the DOM.
The heavyweight champion of the browser.
Absolutely. When a browser loads your HTML, it parses it and builds this massive tree of objects in memory. Every single element, every attribute is an object. That's the real DOM. It's what you see, but it's fundamentally slow to work with because it's tied directly to the browser's rendering pipeline.
So if the DOM is this big, rigid thing, what happens when I just want to change one tiny piece of it?
And that is the critical bottleneck. You change one thing, and the browser often has to do two really expensive operations. First is Reflow.
Reflow, right, where it has to recalculate the layout of everything.
Everything that might have been affected, yeah. And then second is Repaint, where it actually redraws the pixels on the screen. Doing that over and over again is what causes jank. It freezes the main thread.
That explains why older websites felt so clunky. One tiny notification pops up and the whole page seems to lag. So the virtual DOM is really our first shortcut around all that. Let's define it. What is this virtual DOM, and I guess, where does it even live?
That's the key question. The VDOM is not a browser thing. It's a lightweight copy, a representation that lives entirely in memory. You could think of it as a JavaScript scratchpad.
So it's completely detached from the browser's rendering engine.
Exactly. And because the VDOM is just made of plain JavaScript objects, they are incredibly cheap and fast to create, to change, and most importantly, to compare.
Okay, that speed of comparison is the magic ingredient then. It lets React figure out what changed in, like, milliseconds. So let's trace an update. What happens when I click a button?
Okay, so a user action triggers a state change you call setState. At this point, the real browser DOM has no idea anything has happened yet.
So what's React's first move?
First, React creates a brand new virtual DOM tree that represents what the UI should look like now. It's super fast, again, just JavaScript objects. Then comes step 2, which is the real heart of the process.
Yep.
The new VDOM tree gets compared with the previous VDOM tree.
And that comparison is the diffing process.
Precisely. Diffing is just finding the absolute minimum set of changes needed. And this whole optimized process, the diffing, the calculating, that's what we call reconciliation.
So once reconciliation finds those tiny differences, say a class name changed, what's the last step?
The last step is applying the patch. React takes that list of minimal changes and performs a single batched update to the real DOM. It updates only the specific nodes that changed. No full reload.
And that minimizes those expensive reflows and repaints we talked about.
Exactly.
That sounds incredibly efficient. But I've noticed sometimes React doesn't seem to update instantly after every single setState call. It almost feels like it waits a moment.
It does. And that's a brilliant optimization called batching. If you have, say, 3 setState calls that happen very quickly in the same event, React is smart enough not to do 3 separate updates. It waits, batches them all together, and then performs just one single update to the real DOM. It dramatically improves performance by just talking to the slow browser environment less often.
So VDOM is the data structure, the JavaScript copy, and reconciliation is the process that uses it. It runs the diffing algorithm.
You got it. And this is what enabled the declarative API that React is famous for. As a developer, you just say, this is the state I want, and you trust reconciliation to figure out the most efficient way to get there.
I love that. It takes away so much manual DOM manipulation.
It's a huge abstraction.
Okay, now this is where it gets really interesting. Comparing 2 massive trees could be incredibly slow if you checked every possibility. React uses some shortcuts, some heuristics, right? What are the rules?
Right. A brute force comparison would be, exponentially complex. So React makes 3 very clever assumptions that bring the complexity down to a linear, manageable level.
Okay, what's rule number 1?
Rule 1, different element types. If React is comparing 2 nodes and their type is different, like an H1 is now a P, it doesn't even try to see what's inside. It just assumes the entire branch is different. It'll completely destroy the old tree from that point down and build a totally new one from scratch.
So changing an element's type is one of the most expensive things you can do.
It is. It's a signal for a full reset of that part of the UI.
What about Rule 2?
Rule 2, same element type. Now, if the elements are the same type, say it's comparing two div elements, React gets much more surgical. It just looks at the attributes, or props. It will only update what's changed, like a class name or an on-click handler, and leaves the children and the structure alone. This is the ideal, fastest kind of update.
And then there's Rule 3, the one that trips up so many new developers. Lists and keys.
Oh, this is the biggest performance pitfall. Rule 3, list items and keys. When you render a list of items, you need to give each one a stable and unique key prop. If you don't, and you say add a new item to the beginning of the list, React only has the index to go by.
And it thinks everything has changed?
It thinks everything from that point on has changed its content because their indexes are all different now. So it will inefficiently re-render a huge part of the list.
But a key gives each item a stable identity.
Yes. The key tells React, hey, this component is the same one as before, it just moved. So React can just move the underlying DOM node, which is incredibly fast, instead of destroying and recreating everything.
Got it. Keys are non-negotiable for lists. Okay, before we move on to the modern era, let's clear something up. Virtual DOM versus shadow DOM. Are they related?
Not really, other than sharing the word DOM. They do totally different things. VDOM is a framework concept. It's a JavaScript pattern for performance. Shadow DOM is a native browser technology for encapsulation, for scoping CSS and HTML inside web components so they don't leak out.
So one is for speed, the other is for encapsulation.
Got it. Okay, so the VDOM solved the big comparison problem, but it created a new, more subtle one. The whole reconciliation process was synchronous. It was blocking. If you had a really big component tree, that diffing could take, say, 18 milliseconds, freezing the main thread for that whole time. Why was that a problem that led to React Fiber? It was a huge problem for modern user experiences. That synchronous all-or-nothing update meant that if a big update started, nothing else could happen. If it took longer than 16 milliseconds, you'd drop a frame. That's where you get janky animations, misclicks, and a UI that just doesn't feel responsive.
So the problem changed from how fast can we calculate the change to how intelligently can we schedule the work.
That is the perfect way to put it. And Fiber is the answer. Fiber was a complete rewrite of React's core reconciliation engine introduced in React 16. It changed everything.
So what is Fiber, technically? The VDOM is a tree of objects. What's a Fiber tree?
So a Fiber is just a JavaScript object that represents a unit of work. And while it still represents a component tree, it's structured internally as a linked list. The old engine used Recursion to walk the tree, which is really hard to stop once you've started. Fiber's linked list structure turns that recursion into a simple loop of iteration.
And why is an iterative loop better than recursion here?
Because you can pause it. With recursion, you have to wait for the whole call stack to finish. With an iterative loop, React can process one Fiber node, then stop, yield control back to the browser for a moment.
So the browser can handle a user's click or an animation.
Exactly. And then it can pick up right where it left off. That's the core idea of incremental rendering.
That's incredible. It's like an air traffic controller for UI updates.
That's a great analogy. Fiber splits all work into two phases. The first is the render phase, where it's building the new Fiber tree and calculating changes. This phase is interruptible. It can be paused, resumed, or even aborted.
And the second phase?
The commit phase. This is where React actually applies the changes to the real DOM. This phase is not interruptible because you don't want the user to see a half-finished UI, but it's designed to be very, very fast.
So let's talk about that prioritization. Before Fiber, every set state had the same importance. How does Fiber decide what's urgent?
It introduced the concept of priority lanes. So now React can assign different levels of urgency. Things like user input from typing or animations, those are given high priority. They have to feel instant. Then you have medium priority things, maybe data fetching from a network. And then you have low priority, like preloading some off-screen content that the user might not even see.
So if scrolling down a page while a big, low-priority data update is processing in the background?
React can literally pause that data update, handle your high-priority scroll events so the page feels smooth, and then resume the data update when it has a free moment.
Wow.
Right.
And you said it can also abandon work?
Yes. If a new high-priority update comes in, say, the user types something new, React can just throw away the old low-priority work it was doing without ever committing it to the DOM. It prevents rendering outdated information.
That's a huge leap in intelligence.
Hmm.
You also mentioned fiber improves something called hydration. What is that, and why is it important?
Hydration is key for server-side rendering, or SSR. The server sends plain HTML so the user sees something on screen very fast, but it's not interactive yet. None of the buttons work. Hydration is the process of attaching all the JavaScript logic to that static HTML. Before Fiber, this was one big blocking task. The page would look ready, but it would be frozen. Fiber can do this incrementally, making parts of the page interactive as they become ready, which is much better for the user's perception of speed.
This has been an incredible journey. We went from the slow, clunky real DOM to the fast in-memory comparisons of the virtual DOM, and now to this incredibly smart, scheduled world of the Fiber engine.
I think the key takeaway for everyone is that modern web performance isn't just about raw speed anymore. It's about scheduling and prioritization. Understanding that Fiber can pause and prioritize work is what helps you build truly responsive modern applications.
And that leaves us with a final thought for you to take away. Given that Fiber allows for prioritized, interruptible updates, how could you rethink your own app's state management? How could you deliberately separate high-priority state like a text input from low-priority state, like a background data refresh, to take full advantage of this new architecture? That's all for today. If you enjoyed this podcast, please like this video, subscribe to @TechHub, and stay connected for more learning content. Thank you so much for watching. This is a Tech Hub signing off.